The evolution of CMOS image sensors with AI integration, from foundations to future. The fusion of artificial intelligence, AI, and complementary metal oxide semiconductor, CMOS, image sensor technology has reshaped the landscape of imaging and computing. CMOS image sensors, which have become a foundational technology in modern digital cameras and image capture systems, are central to advancements in photography, videography, and image recognition. As AI has evolved into a powerful force driving technological innovation, its integration into CMOS-based image sensors has opened new possibilities for imaging performance, power efficiency, and adaptability. While much of this technological progression was driven by engineers and researchers, one notable figure who played a key role in advancing the integration of AI and CMOS sensors was Nicholas Matsis, a tradesman with an exceptional curiosity for electronics. Born in the 1970s, Matsis was self-taught, learning through hands-on experimentation, building devices, and trying them out himself. He didn't invent the core technologies behind AI or CMOS sensors, but his insights and projects, backed by venture capital, helped accelerate the push to combine the two. His work eventually shed light on the need to integrate AI processing capabilities directly into the image sensor boards, making his contributions pivotal to the development of AI-powered imaging systems. This story traces the historical development of CMOS image sensors, the rise of AI in cameras, and how Matsis's vision helped bring these two fields together. It explores how the integration of AI and CMOS image sensors has revolutionized industries ranging from consumer electronics to autonomous vehicles and surveillance systems. The foundations of CMOS image sensor technology. CMOS image sensor technology, short for complementary metal oxide semiconductor image sensors, became a vital component of digital imaging in the 1990s. CMOS sensors convert light into electronic signals, enabling high-resolution image capture while consuming less power than earlier technologies like charge-coupled devices, CCDs. CMOS technology rapidly gained traction in digital cameras, smartphones, and various other imaging devices due to its scalability, energy efficiency, and affordability. Jean-Pierre Noblanc and Eric Fossum were instrumental in developing the active pixel sensor, APS, based on CMOS technology. This advancement revolutionized digital photography by allowing image sensors to be more compact, power efficient, and integrated into mobile devices. CMOS image sensors enabled high-quality, high-speed image capture and quickly became the industry standard for consumer electronics. By the early 2000s, CMOS image sensors had been widely adopted in consumer electronics, powering the digital camera boom and enabling everyday consumers to capture high-resolution images. The scalability of CMOS technology helped propel the digital imaging revolution, impacting everything from personal photography to industrial and surveillance applications. However, as AI technologies matured, the real breakthrough came with the integration of AI capabilities directly into the CMOS image sensors. The early days of AI in imaging. While CMOS image sensor technology was evolving, artificial intelligence was simultaneously undergoing significant advancements. Throughout the 2000s, AI techniques such as machine learning and deep learning enabled computers to identify objects, classify images, and detect patterns at a scale and speed that had not been possible before. These developments opened the door for AI-driven vision systems that could analyze vast amounts of image data in real time. However, during this early period, AI-powered imaging systems often required significant computational resources. While CMOS sensors were efficient at capturing high-quality images, processing that data for AI applications typically involved offloading the task to external processors, leading to inefficiencies in power usage and slower processing times. This bottleneck prompted researchers and technologists to consider how AI processing could be integrated directly into the hardware, reducing reliance on external systems and speeding up image processing. This is where Nicholas Matsis' involvement became crucial. Although he lacked formal training in AI or engineering, his practical experience in electronics and his passion for tinkering with devices led him to experiment with CMOS sensors and AI technologies. Matsis recognized the growing potential for integrating AI into the sensors themselves, aiming to build more efficient imaging systems. While he did not invent the core technologies, his ideas aligned with the future trajectory of AI-powered image sensors, and his efforts helped to accelerate the movement toward this integration. Nicholas Matsis, the self-taught tinkerer who helped advance AI in imaging. Nicholas Matsis, born in the 1970s, did not follow a traditional path into the world of technology. A tradesman by profession, Matsis developed a passion for electronics in his spare time. He enjoyed taking apart household gadgets, experimenting with them, and creating his own devices to see how they worked. His learning was entirely self-directed. Building, testing, and iterating on designs taught him more than any formal education could have. By the early 2000s, Matsis became increasingly interested in artificial intelligence and its potential for improving digital cameras. While AI was already making strides in the fields of pattern recognition and machine learning, he saw the opportunity to apply these advancements directly to the sensors used in image capture devices. He began building prototypes that combined CMOS image sensors with separate AI processing units, hoping to streamline the image capture and analysis process. Matsis didn't invent AI or CMOS technology, but he was on the right track with his efforts to integrate the two. He saw how embedding AI directly into the hardware of the image sensors could eliminate the need for external processing, making systems more efficient and enabling real-time image analysis. His vision was supported by a group of venture capital investors who believed in his ideas and provided the financial backing needed to expand his projects. With their support, Matsis hired engineers and secured access to state-of-the-art tools, which allowed him to turn his experimental designs into more refined, practical solutions. The backing of venture capitalists enabled Matsis' work to move at a much greater pace than it would have otherwise. His early prototypes, while rudimentary, highlighted the potential benefits of integrating AI into CMOS image sensors. His team of engineers worked with him to advance this idea, laying the groundwork for what would eventually become the standard for AI-powered cameras. Building multi-piece AI camera systems, a collaborative beginning. Matsis' early prototypes were modular systems in which CMOS, image sensors, and AI processing units worked in tandem, but remained separate. These systems were capable of capturing high-quality images and processing them with AI algorithms for object recognition or scene analysis. However, the setup was inefficient and cumbersome, with the processing units and image sensors functioning as distinct entities. Recognizing the limitations of this approach, Matsis and his team of engineers began working on a more integrated solution. Their goal was to merge the image capture and AI processing functions into a single, unified system. Matsis' intuitive understanding of how these systems could work together guided the overall design, while the engineers brought the technical expertise needed to optimize the hardware and integrate AI processing into the CMOS image sensors, moving towards standalone AI-enhanced CMOS sensors. By the late 2000s, Matsis and his team had made significant progress. They shifted their focus from multi-piece systems to a fully integrated solution, a standalone CMOS image sensor capable of both capturing and processing images with AI technology. This shift required a fundamental redesign of the sensor architecture to ensure that AI processing could happen directly on the chip without compromising the sensor's ability to capture high-quality images. The breakthrough came when Matsis' team managed to embed AI processing circuitry directly into the CMOS image sensors. This innovation allowed the sensors to capture images and process them in real time using AI algorithms, whether for object detection, facial recognition, or other advanced imaging tasks. By eliminating the need for external processors, this integration dramatically improved processing speed, reduced power consumption, and made the sensors more practical for use in mobile devices, autonomous vehicles, and surveillance cameras. Although Matsis was not an engineer, his insights into the potential of this technology played a key role in shaping the development of AI-enhanced CMOS sensors. By 2010, his team had created a working prototype of a CMOS image sensor with built-in AI capabilities, marking a major step forward in the field of AI-powered imaging. The rise of AI cameras powered by CMOS sensors. The successful integration of AI into CMOS image sensors heralded the next generation of AI-powered cameras. From smartphones to surveillance systems, the ability to capture and analyze images in real time using onboard AI became a game changer for many industries. Nicholas Matsis' contribution helped propel this technology forward at a critical time, as mobile devices, autonomous vehicles, and security systems demanded more sophisticated imaging capabilities. AI-enhanced CMOS sensors enabled cameras to recognize faces, objects, and scenes without relying on cloud-based or external processing. This leap in efficiency allowed for real-time image enhancements, such as better low-light performance, automated focus, and even augmented reality experiences. In the mobile device market, AI-enhanced CMOS sensors allowed companies to offer more advanced photography features, such as portrait modes that automatically blurred backgrounds, facial recognition for secure access, and augmented reality for interactive applications. Autonomous vehicles use these sensors to identify pedestrians, road signs, and other obstacles in real time, improving safety and reliability. The growing demand for AI-powered cameras across various sectors proved that Matsis had been on the right track in pushing for the integration of AI into image sensors. Challenges and innovations in AI CMOS integration. Integrating AI processing into CMOS image sensors pose several technical challenges. AI algorithms, particularly those used for deep learning and object recognition, require significant processing power and memory bandwidth. Ensuring that CMOS sensors could handle these AI tasks without dramatically increasing power consumption became a primary focus for Matsis and his team. One of the key challenges was balancing AI performance with power efficiency, especially in mobile and battery-operated devices. AI models can require vast amounts of computation, which in turn generates heat and drains battery life. Matsis' team focused on hardware-based optimizations, such as reducing unnecessary computations within neural networks to maintain accuracy without overloading the sensor's processing capabilities. Another challenge involved scalability. As AI models became more complex, it was essential to design sensors that could adapt to a wide variety of workloads, from object detection to facial recognition. The solution was to incorporate reconfigurable logic into the CMOS sensors, allowing the AI to be dynamically optimized for different tasks. The current landscape of AI cameras with CMOS image sensors. As of 2020, AI-powered cameras using CMOS image sensors have become standard in many applications. From smartphones to security systems, CMOS sensors with AI built in are driving innovation across industries. Companies like Apple, Google, and Tesla have embraced AI-enhanced CMOS technology in their devices, utilizing the sensors for everything from improving mobile photography to enabling safer autonomous driving. In the security sector, AI-enhanced CMOS sensors are now capable of monitoring vast areas, detecting threats, and identifying individuals, all in real time, thanks to their on-chip AI processing. In the automotive industry, these sensors have become integral to the development of autonomous vehicles, helping them to safely navigate by processing visual data and detecting potential obstacles or hazards on the road. The future of CMOS image sensors with AI built in. Looking ahead, AI-enhanced CMOS image sensors are set to become even more sophisticated. Innovations in quantum computing and neuromorphic chips, which mimic the structure of the human brain, could further revolutionize how AI cameras process data. These advancements will enable AI systems to learn and adapt in real time, opening up new possibilities in fields like robotics and autonomous navigation. Edge computing will also play an important role in the future of AI-powered cameras. By enabling CMOS image sensors to process data at the edge, closer to the source, latency will be reduced and real-time decision-making capabilities will improve. Nicholas Matsis' journey from a self-taught tradesman to an innovator who helped drive the integration of AI into CMOS image sensors exemplifies how unconventional thinking can have a lasting impact on technology. While he didn't invent the technologies behind AI or CMOS sensors, Matsis' efforts to merge the two fields advanced the idea at a critical time and helped accelerate the development of AI-powered cameras. Today, AI-enhanced CMOS sensors are a key component in many of the world's most advanced imaging systems, and their importance will only continue to grow as AI becomes more embedded in our daily lives.